Axioms are the quiet engines behind every system of thought. They sit at the bottom of our reasoning, not because they are proven, but because something must be accepted before anything else can follow. Whether we're building mathematics, constructing a legal framework, or simply trying to reason about the world, axioms function as the bedrock, those initial commitments that make all further structure possible. Understanding what axioms are, why they matter, and how they shape entire intellectual worlds is essential for grasping how logic, mathematics, and even everyday reasoning actually work. An axiom, also called a postulate, is a statement or proposition that is accepted as true without proof, serving as the starting point for further reasoning or arguments. In simple terms, you can think of axioms as the rules of the game or the building blocks of a logical system. Because you cannot prove everything from nothing, every logical chain must start with some basic assumptions that are agreed upon from the beginning. Key characteristics. Unprovable. By definition, an axiom is not derived from other statements, it is the foundational layer. Self-evident. Historically, traditionally, axioms were considered truths so obvious that they didn't require explanation, e.g., the whole is greater than the part. Arbitrary. Modern. In modern logic and math, an axiom doesn't necessarily have to be true in the real world. It is simply a premise we choose to accept to see what happens next. If you change your axioms, you get a different system, like how changing geometry axioms leads to non-Euclidean geometry. Axiom versus theorem. The main difference is that a theorem is a statement that has been proven using axioms and logic. For instance, in geometry, the Pythagorean theorem is a conclusion that only works if you first accept Euclid's basic axioms. Axioms are the starting points or building blocks for all other ideas. Without them, logic cannot even begin because you cannot deduce a conclusion from nothing. How they function as bedrocks. The unproven foundation. Every logical argument follows a chain of if X is true, then Y must be true. If you trace that chain all the way back, you eventually hit a statement that has no if before it. That final, bottom layer is the axiom, defining the system. Axioms act like the rules of a game. For example, the rules of chess are true within chess. If you change a rule, like how a pawn moves, you haven't disproven chess. You've just created a different game with its own new set of bedrock rules. Necessary assumptions. In fields like science or law, axioms are the untestable assumptions or established principles we agree to accept so we can do productive work. Building up from the bedrock. Once the bedrock, axioms, is laid, you use rules of inference logic to build the rest of the structure. Axioms, the initial assumptions accepted without proof. Logic, the tools or mortar used to connect ideas. Theorems, the complex conclusions, the tower that are proven to be true only if the underlying axioms are accepted. When we say an axiom is true, we aren't necessarily saying it is an objective, universal fact like the sky is blue. Instead, truth in the context of axioms usually means one of three things depending on how you are looking at it. 1. Truth by agreement, the start line. In logic and math, true often just means assumed for the sake of the system. Think of it like the rules of chess. We agree that a knight moves in an L shape. We don't prove the knight moves that way. We simply accept it as a foundational truth of the game. If you change that rule, you aren't playing chess anymore, you're playing a different game. 2. Self-evidence, the common sense view. Historically, philosophers like Aristotle or Euclid believed axioms were self-evident truths, things so obvious that denying them would be nonsensical. Example: A equals A equals A, the law of identity. It feels true because your brain cannot conceive of a world where a thing is not itself. 3. Logical consistency, the internal truth. In modern systems, an axiom is true if it doesn't contradict the other axioms in the same set. We don't ask, is this true in real life? Instead, we ask, is this statement useful and consistent within this framework? Example: in standard geometry, we assume parallel lines never touch. In spherical geometry like the surface of the Earth, we assume they do touch at the poles. Both are true within their own separate systems. In the end, axioms remind us that every system, no matter how rigorous, rests on choices. Some of those choices feel self-evident, some are adopted for convenience, and others are selected simply to explore what new worlds they make possible. But without them, reasoning cannot begin. They are the silent commitments that allow structure to rise, the rules that make the game playable, and the foundations on which every theorem, argument, and conclusion ultimately stands. To understand axioms is to understand the architecture of thought itself.